Okay, so in this video, we're going to look at partial sums and telescoping series. So the directions here are to find a formula for the nth partial sum and then use it to determine convergence. So I'm going to do these two examples here. So I'm just going to jump right into it. Okay, so with some of these types of examples, it's like obvious that you have a telescoping series, right? So one thing minus the other thing, and this is one integer higher than this. So a lot of times the easiest way to determine your partial sum when it's obvious that this is a telescoping series is to just start writing out a few terms and just see if you notice a pattern. So if I just start plugging in numbers, so I have tangent of 1 minus tangent of 0 plus tangent, maybe I'll put parentheses around this. So there's the first term. And then the next one, this will be tangent of 2 minus tangent of 1. And then the next one will be tangent of 3 minus tangent of 2. Okay, so we can already kind of see a pretty clear pattern establishing itself. So then what would happen with the n minus 1th term? So for the n minus 1th term, this would be tangent of n. Let's see, actually, I'll go to the next line. So this would be tangent of n minus 1 minus tangent of n minus 2. And then what would the nth term be? The nth term would be tangent of n minus tangent of n minus 1. So I bring this up because you might want to blow this out a little bit just to make yourself confident of the partial sum that you're writing up. So what I notice, right, is that so these tangents drop out, right? And then tangent of 2 drops out. So tangent of 0 is going to have nothing to cancel itself out with. But we know then from this pattern that tangent of 3 will. Now, if this pattern doesn't seem obvious to you, you can write out more terms too, right? You could write out 5 terms if that's helpful for you. But I feel like I've got a decent handle now on this. And so if I continue going through, so the tangent of n minus 1s I know are going to drop out. And then also this tangent of n minus 2, that'll drop out from a previous sum. So the only things that I'm left with then are going to be tangent of n minus tangent of 0. Tangent of 0 is just 0, so this is just going to leave me with tangent of n. So this is the partial sum that I was looking for. Okay, so now I'm going to use this to determine convergence, so I'll make some space. Okay, so to determine convergence, now I want to take a look at the limit as n approaches infinity of tangent of n. Well, this is just kind of bouncing all over, actually. So this does not exist. And so since this does not exist, we're going to say then that the series diverges. So there's our conclusion there. Okay, so for the other example that I've chosen something that doesn't look like a telescoping series. But what I notice is, so I've got 2 factors. And so, if you've learned anything from integration, right, when you can factor the denominator and you can't go any farther with simplifying, you probably get to use partial fractions. So this type of problem right here is just screaming for partial fractions. So let's roll up our sleeves and remind ourselves, how the heck do you do that? All right, so I've got 2 linear factors. So for each linear factor, they get a variable. So the first factor will get A, and the second factor will get B. Now I do have a whole video where I break down partial fractions, so I'm kind of assuming that you know the basics of it, but if you want to see a full explanation, you can check out my video on that. Okay. So now the idea behind this is that I multiply this denominator to this side. And so when I do that, what ends up happening? Well, we have some cancellations. So when I multiply this denominator times the first fraction, so let's see, this will leave me with just 6 on this side. So this times this, the 2n minus 1 will cancel out. So I'm just left with 2n plus 1. And then for the other one, I'll be left with 2n minus 1. Okay. So then, where do we go from there? Well, I want to rewrite this as, let's see, I'm sorry. Okay, so the things with the n terms, this is the way I like to do this. So I like to factor out the n, and then what would I be left with? So here, if I factor n out of this, I'm left with 2 times a. So this will be 2a. And then 2n times b. So if I factor out the n, that'll leave me with 2b. And then the constants, I'll write the constant as n to the 0. So 1 times a, and then negative 1 times b will give me minus b. This is just the way that I like to do this. There's a couple different ways that you can do this. Okay, so what this allows me to do now is I can set up a system of equations. So I'll clear some space. So I need to set the constants equal to the constant on this side. So there's only one constant, so this will be a minus b equals 6. And then anything that has that goes to just the ends, I will set that equal to the ends on this side. Now there are no ends on this side, so what I'm going to do then is I'm going to just set 2a plus 2b equal to 0. And now I have to solve this system here. And so let's see, how do I want to do this? Why don't I multiply everything here by 2 so that I get 2a minus 2b equals equals 12, sorry. And then I can add everything down to get 4a equals 12, so that implies that a equals 3. And so then I have 3 minus b equals 6, so negative b equals 3, so b will equal negative 3. Okay, so now I can set up the fractions that I have, so I'll just clear a whole bunch of space. And I can rewrite this sum. This will now be, instead of, so I can replace the a was 3, so this was 3 over 2n minus 1, and then we add negative 3 over 2n plus 1. So here is my new series. And this is a little bit more obvious. Actually, I can move this negative here. This is now much more obvious that this is a telescoping series, right? Because this is the same numerator, and then the denominators are clearly kind of flipping back and forth a little bit. Now, one thing I can do to make my life easier, I could factor out the 3, so I'm going to do that. And then I can just take a look at what's going on with these terms here. So once again, if you don't quite know what the pattern is going to be, you can just like write it out. So I'm going to ignore the 3 for a second. I'll just maybe write the 3 here so I don't forget it. But okay, so let's just start plugging in numbers. So if I start with n equals 1, so this becomes 2 minus 1. So this is just 1 minus, and then this is 2 plus 1. So this will be 1 minus 3. I'll put some parentheses around this. Okay, and then let's go to the next term. So n equals 2. So this will be 4 minus 1. So that's 1/3. And then 4 plus 1, which is 5. Okay, so now a pattern's emerging, right? So then the next one, n equals 3. This will be 1/5 minus 1/7. Okay, and now I'm already feeling pretty confident about the pattern. So if I do just 1 over, we'll just do n here, I guess. I think I feel pretty confident about this. But you can write out more terms if you want to. I'm also just kind of trying to save space here. Okay, so this is a telescoping series with just odd numbers, right, in the denominator. So as far as like what's going to get canceled out, so just about everything's going to get canceled out except for the very first and the very last terms. So I can pretty confidently like see what's going on here. So my partial sum is going to look like this. 1 over, let's see, actually this is 1 minus 1 over 2n plus 1. Okay, so I'll make some space. So I just went ahead and redistributed the 3 back in and wrote this as a partial sum just to make it look nice. So ultimately, to determine convergence, now I need to take the limit as n goes to infinity. And this one's actually a pretty simple one to figure out, right? Because this is just going to go to 3, and then this is going to go to 0. So this equals 3, which means that the series converges. Okay, and so that's your crash course on working with telescoping series. So hopefully that was helpful. If it was helpful, consider hitting the like button. I'll catch you guys in another video. Thanks for watching.